Hello, I'm Sarita, and in this lecture, I will be discussing about the late evolutionary stages of stars. We will start first with giant stars. So, giant stars are comprised of red giant branch stars, the asymptotic giant branch stars, as well as the supergiant stars. Just as a recap, red giant branch stars are luminous giant stars of low to intermediate mass stars, that is 0.3 to 6 solar masses with inflated envelopes, and the surface temperature is low of the order of 3000 to 5000 Kelvin, and these are in the interior, these are fusing hydrogen to helium in a shell, and they have inert helium cores. This stage lasts around a billion years. The asymptotic giant branch stars are later evolutionary stages than red giant branch stars. They are very luminous and have thousands of times the luminosity of the sun. In the interior, they have a double shell burning phase where one shell is fusing helium to carbon, and there is another shell fusing hydrogen to helium. And these have inert carbon oxygen cores. The third group of giant stars is the supergiant stars, which are the late stages of massive stars. They are in the pre-supernova stage and they are very luminous. In all these stages, there is an inflated envelope and the surface gravity is very low, and consequently there is an enormous amount of mass loss which occurs in these stages. Since these stars are relatively large in size, it has been possible to do direct imaging of these kind of giant stars, which is shown in the panel below. So, one can see that there are two small dots shown towards the center, which indicate the sizes of the main sequence stars, and the size of the giant stars and supergiant stars are shown as red circles on the right, and on top of this are shown the actual images taken at different wavelength bands, optical as well as millimeter. These represent direct images of the giant stars. Usually for stars, we are unable to resolve out stars and we see them as point-like objects because of the limitations of our observing techniques. However, giant stars being much larger in size, it is possible to image them directly. So, we start off with examples. So, this is an example of a red giant star called Mira, also known as Omicron Ceti. This is located at a distance of 300 light years, and its spectral type is M73. So, M is the cool spectral type or the latest spectral type, and 7 is the spectral subtype, and 3 represents the luminosity class. The effective temperature of this red giant star is around 3000 Kelvin. It is around 1.1 solar mass. Its radius is around 350 solar radius, and its age is estimated to be 6 billion years. So, one can see on the left Mira and its companion on top. This is again a part of a binary star system, and below panel shows the star Mira in visible as well as in ultraviolet. One can see that in ultraviolet there is a small tail-like structure. The ultraviolet images taken of Mira using Galax shows that there is a substantial amount of mass loss, and this gas which is lost is also very bright because it is hot and it shines in ultraviolet, and it extends to quite a distance from the star. So, the top panel on the right shows the ultraviolet image, and the bottom panel shows the visible, where the Mira can be seen as a very bright spot. There is also a thermal pulsations observed towards this star Mira, and in fact it has given rise to an entire class of variables known as Mira variables. So, the panel here shows the variability observed towards Mira. Next, we come towards the asymptotic giant branch stars. These asymptotic giant branch stars are stars which have a very extended envelope, as explained earlier. one of the interesting things about the stars is that the outer envelope is so cool that not only molecules are formed, but it is believed that submicron sized dust particles are formed in the outer envelopes of the AGB stars. And the effect of the radiation pressure is to push these dust particles into the interstellar medium, and it is largely believed that most of the dust that we observed in the interstellar medium, that is the medium between the stars, is processed and generated in the outer envelopes of asymptotic giant branch stars. This slide shows an example of the dust generation and production. So, this is the picture shows the dust from the AGB star W Hydrae. Here, this is an ALMA image, and one can see that it is a combination of red and yellow images. The red shows the location of silicon oxide molecules, and the yellow shows the region of the aluminum oxide. These are two important ingredients found in interstellar dust. While the silicon dioxide is found to extend to very large regions, the aluminum oxide is very close to the star. This helps researchers understand the process of dust formation in the envelope of the asymptotic giant branch stars. An example of a supergiant star is Betelgeuse, one bright star in the constellation of Orion. These stars are very large in size, and what is shown in the left panel is an artistic impression of the supergiant stars as well as the mass loss which is seen from the star along the scale of the solar system. So, on the left panel there is a line, a vertical line which shows the scale of the solar system. And for example, the size of this supergiant star Betelgeuse is found to extend to Jupiter, and the mass loss extends still much larger distance, approximately 30 AU. And on the right is shown a panel of an actual infrared picture of the supergiant star Betelgeuse. This is a combination of two pictures. The outer flame like structures which are seen in the image, gas and dust shells which are thrown out by the supergiant star, which is seen as a dot in the center. And to image this flame like structure, one had to mask out the central regions which are very bright, and that appears as this black disk which is seen at the center. The supergiant star Betelgeuse, which appears as a dot, is an alternate image that is superposed on this image to show us the location of Betelgeuse. We next move on to understanding about planetary nebulae. So, what are planetary nebulae? These are expanding shells of gas around a white dwarf progenitor. This name is a misnomer because these, although they are not associated with planets, they are called planetary nebulae because first observed by telescopes, it was thought that they resemble gaseous planets. Planetary nebulae emit in ultraviolet. This is because these represent the outer envelopes of the star, which are ionized as well as excited by the ultraviolet radiation received from the white dwarf stars. In optical images, they are found to have vivid colors. For example, the bluish green, which is because of oxygen lines and neon lines, and the reddish hue is because of H alpha as well as nitrogen. It is found that these planetary nebula have very complex but symmetric structures. So, some pictures of planetary nebula that have been observed by the Hubble Space Telescope are shown in this slide. One can see that they have very symmetric structures, and the color hue indicates the different species of ions that are found in those regions around the nebula. Most of these planetary nebula are also found to have a dot at the center, which is the white dwarf that has been imaged at the center of the planetary nebula. These have very symmetrical structures, and there is lot of work in trying to understand what gives rise to this complex symmetries. This is in many cases it is found that varying viewing angles and multiple ejections, not just one ejection of the envelope but multiple ejections from the stellar surface could give rise to these symmetries. In addition, the presence of a binary companion or the presence of magnetic field could also give rise to these complexest symmetries. On smaller scales, it has been found that bright cometary knots are seen close to these planetary nebulae. This represents gas moving at very high velocities away from the star of the order of 30 to 40 kilometers per second. The estimated age of the planetary nebula is around 10,000 to 50,000 years, and currently around 1500 planetary nebulae are known in our galaxy. This picture shows a planetary nebula called Helix Nebula in the optical and the near infrared. So, the left side of the image is the optical image, which is mostly from the ionization and excitation of atoms, whereas the right side of the picture shows the same nebula but in near infrared. As one can see, the near infrared picture shows cometary knots, and these the emission in near infrared is mostly due to the presence of cool dust as well as complex molecules, unlike the optical. This panel shows spectra taken towards two planetary nebulae. The left side shows the spectrum of a planetary nebula in NGC 1501. NGC is a catalog of nebulous objects, and one can see a number of emission lines, and these are high excitation and high ionization lines. For example, one can see O6, O3 and ionized helium, ionized oxygen lines. On the right is another planetary nebula, Sextant A, and again one can see that there are a large number of emission lines towards this nebula. Based on these excitation lines, people try to derive the physical conditions in the nebula and understand the evolutionary stages. Although planetary nebula have been observed in different parts of the galaxy, in order to get an estimate of ages of these planetary nebula, one area of research is to associate the planetary nebula with a given cluster. So, this work, for example, shows a planetary nebula Abell 8, and the researchers Turner et al. Have tried to associate this with a cluster called Bika 6. The planetary nebula is seen as a ring-like structure in the left side image, and on the right side image we can see an HR diagram where one can see the main sequence stars of the cluster as well as the stars which have evolved off the main sequence. The central star of Abell 8, as one can see, lies in the white dwarf region of this HR diagram. We next move on to trying to understand about white dwarf stars. So, what are white dwarf stars? These are hot stellar degenerate remnants of low mass stellar evolution as well as intermediate mass stellar evolution. So, the main sequence stars which of mass up till 8 solar mass generally undergo mass loss and end up as white dwarf stars, and the first white dwarf star to be discovered was Sirius B, which is the companion of Sirius A. The panel here shows the images of Sirius A and B. The left side shows the optical image and the right side shows the X-ray image. In the optical image, one can see that Sirius A, the bright star that we see, is very bright, in fact nearly 1000 times brighter than Sirius B, whereas in the X-ray image Sirius B is much brighter than A. In fact, a careful study had shown that Sirius B was an exotic star, and a further scrutiny led to our understanding of this Sirius B as a white dwarf star with degenerate matter. The white dwarf stars have a higher effective temperature because although there is no nuclear energy generation happening in the white dwarf stars, but they have a lot of heat which is radiated out. As time passes by, these white dwarf stars cool, and these are faint low luminosity objects, and therefore they lie towards the lower side of the HR diagram. A spectral analysis of white dwarfs have shown that white dwarfs can also be classified according to their spectra. Although the white dwarf is given a spectral classification of D, there are various subtypes that are observed, and these are given alphabets A, B, C, Q and Z. For example, one can have a white dwarf which is DA or DB or DC. Now, what are DA type white dwarfs? These represent white dwarfs which have only pressure broadened hydrogen lines. No other lines are observed, and nearly 2/3 of known white dwarfs are found to be of DA type. And DB type white dwarfs are those where only helium absorption lines are observed and hydrogen lines are nearly absent. Around 8% of known white dwarfs are found to be of DB type. The DC are those where only continuum is seen and no absorption lines are seen, and 14% of the known white dwarfs are found to be of this category. Then one has also found white dwarfs which are a bit different, and these are given the nomenclature of DQ and DZ. DQ if carbon lines are seen in the spectra, and DZ if heavy metal lines are seen in the spectra of white dwarfs. This panel shows the spectra of white dwarfs. On the left panel, one can see the 4 DA white dwarfs in the globular cluster NGC 6397. This spectra are in the optical regime, so the Balmer lines are clearly seen. And on the right hand side, the optical spectra of known white dwarfs in the having spectral types DB, DC are also shown. What is the origin of these different spectral classes of white dwarfs? In the case of a DA type, as hydrogen lines are prominently seen, it is believed that the matter gets vertically stratified, because in a star it is made up of hydrogen, helium and other trace elements. After it has reached the white dwarf stage, it is believed that a vertical stratification of matter takes place and the heavier elements move down, whereas a hydrogen moves near the surface. Consequently, when a spectrum is taken, the outer hydrogen is responsible for the absorption lines seen in such white dwarfs, and it is believed that this happens on relatively fast time scales of the order of 100 years. The origin of non-DA type white dwarfs is probably mass loss and stripping of either mass loss, that is stripping of hydrogen from the surface. Alternately, it could also be because of convective mixing. That is, if carbon lines are seen or metal lines are seen, these have been brought to the surface because of the convective mixing of the outer layers. There is also a special category of white dwarfs which are pulsating, and these are known as ZZ Ceti variables after ZZ Ceti white dwarf, and this is because of pulsations, radial pulsations in these white dwarfs. These kind of variable white dwarfs are given the classification V. So, for example, one can have DAV as a variable DA type white dwarf. And it is believed that partial ionization zones are responsible for the changing opacity and hence the radial oscillations. Now, the cores of the white dwarfs are degenerate, and the degeneracy relation is given as pressure is equal to K1 a constant times the mass density by mu E raised to the power 5/3, where mu E is related to the average number of electrons per nucleon. One consequence of this non-relativistic degeneracy pressure is that there is a maximum mass to which the white dwarf can be supported, and this has been found to be 1.4 solar masses. And if the mass of the white dwarf exceeds 1.4 solar masses, then the electrons become relativistic. They are degenerate but become non-relativistic. However, this kind of matter is highly unstable and it undergoes collapse. And another consequence of this degeneracy pressure is a mass volume relation. It has been found that the mass multiplied with the volume of white dwarfs is constant. That is, mass is inversely proportional to volume. Higher the mass of the white dwarf, smaller is the volume. This can also be understood from our understanding of the degeneracy pressure. More the mass the white dwarf has, the denser it should be in order to generate higher degeneracy pressure. We next look at this category of stars known as neutron stars. These are remnants of high mass stars, the cores which are supported by neutron degeneracy pressure. The existence of such kind of stars was first proposed in 1934, and as neutrons are also spin half particles, it is believed that they are responsible for the hydrostatic equilibrium which is holding up the neutron stars. In these cases, the matter is very dense, and the densities can reach as high as 10 power 17 kilogram per meter cube. For white dwarf stars, this one can imagine that if the mass is of the mass of the sun, then the size of the white dwarf will be roughly the size of the earth. That gives us an idea of the density of the white dwarf star. In case of neutron star, if one assumes that the mass of the star is greater than 1.4 solar masses, the size that one is expected to have, so that neutron degeneracy pressure supports it, is expected to be around 10 to 15 kilometers, which means that the matter is extremely dense. That is, it can exceed the atomic density. So, if we consider a neutron star whose mass is 1.5 solar masses, then the surface gravity is of the order of 10 power 12 meter per second square, and the escape velocity is a high fraction of the velocity of light. Now, what is the structure of these kind of neutron stars? One needs to understand the equilibrium configuration of the nucleons that are present, as well as electrons that are present, because these are neutral, as well as some iron nuclei that are present. So, there are a lot of models to help us understand the structure of these neutron stars, because the nature of matter at such high densities is not known to us. So, the proposed structure of the neutron star is shown here, and one can imagine a neutron star to have various layers, outer crust, inner crust, and which is shown in the left hand side panel, and the anticipated densities are also listed. You have an interior which is a superfluid of neutrons, protons, and then a core where the matter density is so high that we are not certain of the various particles that are present there and the particle interactions that are possible. The table on the right hand side lists the constituents of the various layers. For example, the outer crust is made up of mostly iron nuclei, non-relativistic free electrons, and as you go inward, these electrons become relativistic. And in the inner crust, one can see that there is neutron rich nuclei, and this is supported by neutron degeneracy pressure. And as one goes towards the core or the center of the neutron star, the densities become so high that the various particles are produced, and one needs to have a better understanding of the physics in these regions. Similar to the white dwarf stars, the neutron stars also have a mass volume relation because they are supported by the degeneracy pressure of the neutrons. Again, the more massive a neutron star, the smaller the volume it will occupy. And modeling has suggested that the upper mass limit for a neutron star is around 2.2 solar mass for a non-rotating neutron star, and for a rotating neutron star it can be higher, of the order of 3 solar masses. And if the mass of the core is larger than 3 solar masses, then even the neutron degeneracy pressure cannot support the collapse, resulting in the formation of a black hole. There are two properties of neutron stars which were anticipated and later found. First is, it was expected that these kind of neutron stars would have a rapid rotation. This is because of the conservation of the angular momentum. Before the formation of the neutron star, the massive star passes through a supergiant phase. If the supergiant is found to be rotating slowly, then it is expected that when it contracts and forms a neutron star which is very compact, then it would be rotating very rapidly. The other property that was anticipated was that it would have a very high magnetic field because of the conservation of magnetic flux. So, now we come to this class of objects known as pulsars, and as we will see, these pulsars represent neutron stars which are rotating as well as have high magnetic field. So, how were these objects first found? So, Jocelyn Bell and Anthony Hewish in 1967 were setting up a number of radio dipole antenna in the English countryside, and they found that there were certain blips which were very regularly spaced, and after eliminating all sources they realized that this is actually from a cosmic source. They were puzzled because these were separated by very precise duration of 1.337 seconds. This pulsar we now know is the pulsar PSR 1919 plus 21. At that time, various models were proposed to understand the nature of these precise pulses. This included binary stars, pulsating stars, and rapidly rotating neutron stars. Based on the period of pulsation, the binary star and the pulsating star ideas were discarded, and it is now known that these pulses arise due to the rapid rotation of neutron stars. Currently, more than 2000 pulsars are known, and observations of these pulses of light have been carried out across a range of wavebands, and the pulse duration varies from milliseconds to tens of seconds. This is a simplified model of our understanding of how the pulses of light are generated. So, in this figure, for example, one can see the neutron star at the center, the spin axis is shown, and the magnetic axis, which is distinct from the spin axis, is also shown diagonally. Now, when the neutron star is rotating very rapidly, the magnetic axis also rotates. The magnetic field is a dipole field, and one can imagine the magnetic lines shown in blue in the panel. Now, along the poles, magnetic poles, the magnetic field is very high, and it is expected that the relativistic electrons which are present in the outer regions of the neutron stars can get accelerated relativistically around these magnetic field lines, and in the process generate a synchrotron radiation. And therefore, what we see as pulses is the outcome of the synchrotron radiation near the magnetic poles. As the magnetic axis is rotating about the rotation axis, the pulse of light also seems to rotate, very much like what one observes in a lighthouse. I would like to reiterate that this is of course a very simplified model, and research has shown that pulses are far from simple. They have various structures, and the pulse duration varies. So, a number of effects need to be considered in order to understand the radiation emission mechanisms and the structure close to a neutron star. Now, some of the basic properties of the pulsars are listed here. Most pulsars have periods between 0.25 seconds, that is few milliseconds and seconds, and they have extremely well defined periods. That is the pulses are precise up to 15 to 17 decimal places. This is because the pulse duration is very short, and the time period between the pulses is also short, allowing us to make innumerable measurements or a very large number of measurements, giving rise to these precise time periods. In addition, it is also found that these periods are slowing down with time of the order, or that is p dot, that is the rate of change of period is of the order of 10 power minus 15. Below what is shown are the pulses observed from 3 pulsars at radio frequencies, and each panel shows the pulse shape at different frequencies. One can see that at different frequencies the pulse shape is slightly different, and other effects need to be considered in order to understand this change in the shape of the pulses. We now go on to understanding about supernovae. So, what are supernovae? These are transient explosive events. There are historic records of supernovae when certain bright stars were found to have brightened by many orders of magnitudes. For example, the supernova in 1006, that is called AD 1006 supernova, then the Crab supernova which happened in 1054 AD, and the most recent closest supernova was the supernova 1987 A. A represents the first supernova of the year. This happened in the Large Magellanic Cloud, which is an irregular galaxy, our neighbor, located around 50 kiloparsecs from us. The supernova have also been classified based on both their spectra and light curves. So, they were first classified as type 1 and type 2. This type 1 and type 2 classification is based on the spectra taken during the supernova explosion. So, the type 1 supernova do not contain hydrogen absorption lines, whereas the type 2 supernova contains strong hydrogen absorption lines. Further, it was found that type 1 could be subcategorized into A, B and C. So, type 1A represents that class of supernova which have strong silicon absorption lines in the spectra. Type 1b represent those which have strong helium lines, and type 1c are those which do not have strong helium lines in their spectra. And this classification is evident in this slide on the right, and the spectra of the various classes is shown in the left panel. For example, the top spectra is supernova type 1a, and which type 1a, which does not show hydrogen lines, but it shows the silicon lines, absorption lines. Then the next one is the supernova type 2, and one can see that there are strong absorption lines, the H alpha, H beta, H gamma. There are also other lines, and type 1b and type 1c are shown below. And one can see that there are helium lines in 1b which are absent in 1c. This slide shows the light curve of the supernova. As these are transient explosive events, we measure the brightness as a function of time. The left hand panel shows the type 1 supernova light curve, and one can see that it has a very characteristic light curve. The radiation from the supernova increases, it reaches a peak and then falls down and then falls more slowly. On the right hand panel, we see the type 2 supernovae, but the light curves again show a distinction. One can see that there are type 2p supernovae as well as type 2L supernovae. So, the P represents the plateau in the supernovae light curve. So, one can see that there is a plateau. Variations in the light curve are related to the radioactivity and genesis of nuclear elements during the supernova phase. During this supernova, an enormous amount of energy is released, making the star brighter than even the galaxy. It is anticipated, and it has been found that nearly 10 power 46 joules of energy is released, but not all of it goes in radiation. Only around 0.01% of this energy is released as radiation. 1% of this energy is believed to be responsible for the kinetic energy of the ejected material, and the rest of the energy, more than 99%, is in the form of neutrinos. In fact, the neutrinos from cosmic object other than the sun was for the supernova 1987A from the Kamiokande detector in Japan. We now know that supernova type 2 as well as type 1b and 1c are related to the evolution of a single massive star leading to the formation of a neutron star. That is, these classes of supernova represent the core collapse supernova as explained earlier. What explains the type 2 versus type 1b and type 1c for the core collapse supernova? The type 2 have the hydrogen absorption line, so it is believed that these arise because of explosion of the supergiant star as a supernova. However, type 1b and 1c do not have hydrogen in their spectra, and it is believed that this is because of the loss of hydrogen from the envelope, probably because of mass loss. The type 1 supernova, on the other hand, is not associated with the evolution of a massive star. This result has been arrived at because these type of supernovae have been observed in a large number of galaxies where massive stars are either not present, or if they are present, are expected to be in very small numbers. Therefore, it is believed that type 1a supernova is not due to the core collapse of a massive star. We now associate type 1a supernova with a white dwarf system, that is a white dwarf in a binary system, and when this white dwarf takes in material, accretes material from the companion, then it can become massive and it can explode as a supernova in the later evolutionary stages. So, this slide shows the Crab supernova remnant. Supernova remnant represents the nebulous surroundings of the progenitor, that is the neutron star or the black hole. That is, it represents the energy transport of the supernova to the surrounding interstellar medium, which becomes so hot that it emits in X-rays, ultraviolet and a whole range of wavelengths. Here what is shown in this panel is the Crab supernova remnant, and at the center one can see the Crab pulsar. The vertical panels on the right shows an enlargement of the two stars seen at the center, one of which is the Crab pulsar. Therefore, one can observe that one of the stars brightness remains constant, whereas the brightness of the pulsar is increasing with time and then decreasing, which indicates the pulsating nature of the Crab pulsar. The Crab supernova remnant in this panel is shown across a range of wavelength bands from radio to infrared to visible light to ultraviolet. X-rays is shown in the middle panel below, and then gamma rays. One can see that this Crab supernova remnant looks very different in different wavelength bands. This is because in different wavelength bands, the emission that is being received is the result of certain characteristic physical processes. Therefore, by studying a particular object in a given wavelength band, one can understand the physical processes associated with that wavelength regime. In X-rays, for instance, one can clearly see the jet-like emission from the Crab pulsar as well as a disc-like structure around it. This shows a number of supernova remnants. Crab is shown in general, 3C48 is shown in the panel below, and also the Tycho supernova remnant is seen as a spherical remnant on the right side of the image. Now we go to the other class of compact objects known as the black holes. So, black holes represent the ultimate gravitational collapse of a massive star. Now, it is expected that if the initial mass of the star is greater than 25 solar masses, then it will result in a black hole because it exhausts all the sources of nuclear fusion and the mass of the core is sufficient for it to overcome the neutron degeneracy pressure. Black holes are usually described by a spherical surface known as the Schwarzschild radius. It is also known as the event horizon because light cannot escape this radius and no information can be received about the black hole or from within this. In other words, light is frozen in time at this radius. This Schwarzschild radius is given by this relation Rs is equal to 2gm by c square. Black holes are generally described as a singularity within the Schwarzschild radius. One can also estimate the mass of a black hole based on the gravitational influence of the black hole on other objects, the other stars in the vicinity. And black holes based on their mass are categorized into three types. One is the stellar mass black holes, the intermediate mass black holes, and the supermassive black holes. So, the stellar mass black holes generally are found to have masses between 3 and 15 solar masses. It is believed that these are the result of the core collapse of massive stars. However, there are black holes which are found to have masses in the range hundreds to thousands of solar masses. These are called intermediate mass black holes. These are likely to develop in the course of dense environments such as globular clusters, either through the through supermassive stars, through the collapse of supermassive stars, or the mergers of stellar mass black holes. Then there is the supermassive black holes which are found at the centers of the galaxies, and these are found to have masses of the range 1 million to 1 billion solar masses. And in fact, most of the galaxies are now believed to harbor black holes at their center. It is believed that these black holes probably formed due to collisions between the galaxies, or they could be an extension of the intermediate mass black hole. Even the Milky Way has a supermassive black hole at the center whose mass is of the order of 3.7 million solar masses. This is the first picture of a supermassive black hole that has been taken very recently in April 2019. This shows the center of the galaxy M87, and this has been carried out by a large collaborative effort in the Event Horizon Telescope collaboration. And with this, I stop. Thank you.